Okay, so hello everyone. So I'm Leo, and I will talk about one of my long-time projects that I've made about Rust. So it's RustLex, a lexical analysis generator in Rust that generates Rust. So I wasn't sure about whether I should do this talk or not because I lose some motivation in this project recently, but anyway, Axel wanted me to to do it, so let's go. I won't assume that everyone here knows what a lexical analyzer generator is, neither what a lexical analyzer is. So first, what is a lexical analyzer generator? It's a generator for something that is a part of a compiler. So why do we generate parts of a compiler? A compiler is made of several parts. You have the front end that takes the raw inputs from your program and that will pass it into an internal representation which is called an abstract syntax tree, which is a tree representing your program. Then on this tree you run a part that is called a middle end that will run various analysis passes. And then once you analyze your tree and check that it corresponds to a valid program, you can generate intermediate code with it and then optimize it and generate native machine code. So when you create a new language, basically you don't want to worry about all those spaces. The backends and frontends of the compiler are difficult to write, and it's not the most interesting part. When you're writing a compiler, what you focus on is the semantics of your language. So what analysis passes you will do, what programs you will reject, why. So the most interesting part of a compiler is obviously the middle end. So there have been needs for a long time to abstract over the less interesting parts of a compiler that are the front end and the back end. For the back end, for many years now, we have LLVM. There is also GCC, but its API is not as usable by other compilers as is LLVM. And for the compiler front end, we have Lexers and parsers generators. So the goal is to abstract over the first pass of a compiler, whose goal is to pass the inputs into an abstract syntax tree internal representation. So a compiler front end is also made of several parts. First, you have the program input, which is a raw stream of characters. And the first pass is called a Lexer, which it stands for lexical analysis, and it will split the raw stream of characters into tokens. A tokens is like a word of the language, if you want an analogy with the natural languages. And once you've got a stream of tokens, you can make a tree out of them. So make sentences with those words, and this is the work of a parser. And then you've got the abstract syntax tree. We have generators, which are programs that generate the Lexers and the parsers from a set of rules. Yak is a tool that has existed for a long time, and that generates a parser from a set of rules, and Lex generates a Lexer. So you give to those tools rules that describe how you want to split character into words and how you want to make trees out of tokens, out of words, and they will generate C code out of it. C code to which you will give the inputs, and that will give you an abstract syntax tree. Why did I choose to write RustLex? Because C is really bad for writing compilers. I don't know if you already wrote C codes that did a lot of manipulation on strings. It's just super painful to write. You have to deal with buffer management, and it's really bad to write compilers on this kind of things. Rust is great. We have some types, we have pattern matching, we have an LLVM binding that is used in the standard Rust compiler. So Rust could be a great language for writing compilers, although what's miss is lexers and parsers generators. So I chose to do one, despite that there is already a Rust backend for Rego, which is 100 times better than the thing I wrote. But anyway. And finally, Rust syntax extensions are a really great tool to create small domain-specific languages with Rust. How does Lex work in the first place? Lex has its own language, the Lex language. It's a language in which you describe lexing rules, and you run Lex on your Lex file. Lex will parse it and generate C from it. It's not very good to integrate with the rest of your compiler. And the programming tools like syntax highlighting or other editor features work especially bad with Lex. Syntax extensions are a Rust feature that allow you to create some kind of a compiler plugin. It's compiled dynamic library that consists of compiled Rust code that will be loaded by the Rust compiler when you invoke some macros, and the compiled code that is inside the library will be run to expand the macro invocation. So it will receive from the Rust compiler a syntax tree that describes the arguments you pass to the macro. It can run arbitrary Rust code and return another syntax tree that represents the expanded form of the macro code. So it's easy to integrate anywhere in the Rust code, and it works well with tools. So let's see an example. This is what RustLex invocation looks like. So you call the RustLex macro. At the top of your crate, you will have to write something like face syntax, external crate RustLex, which tells the compiler to load the RustLex plugin. And then you invoke the RustLex macro this way, and you write your RustLex code. So it looks a bit like Lex, with a more rusty syntax. You write a set of rules. Each rule describes how to create one kind of token. So what you see before the arrow is a regular expression. It has a particular syntax for regular expressions. But this was mainly to integrate with the Rust syntax so that syntax highlighters and such will work on regular expressions. And also to make it easy to include escape characters inside your regular expressions. I don't know if you already used regular expressions library in common languages, but sometimes it's awful. When you want to include a backslash, you must backslash the backslash. But if you backslash the backslash will be interpreted by the syntax for strings of your host language and not by the regular expression engine. So you have to send two backslashes so that the regular expression engine will receive it. So you write something like backslash, 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 backslash. And you end up with huge quantities of backslashes. So when you use these kind of things, you don't have this problem. You have standard literal character syntax, just like in the rest of the language. And you don't have to worry. The rules for backslashing are the same. And in regular expressions, you backslash quite often because you want to use tokens that are reserved operators like the star for the clean closure, the dot operator. So when you use character literal-like syntax, you don't have to worry about this. You don't have to backslash anything. You just, so here, if we take an example, the hyphen stands for character sequence, but if you put an hyphen between quotes, it will be the hyphen character, no surprise. So this describes a simple analyzer that recognizes 3 types of tokens. When it is a sequence of 1 or more digits, it will say that it just saw an integer. A sequence of alphanumeric characters beginning by a letter or an underscore is an identifier, typically a variable name. And finally, int just matches the int keywords if you want to distinguish it from an int identifier, because int matches both rules. So when there is an ambiguity, lexical analyzers, like RustLex but also Lex, will always try to match the longest input as possible. So for example, if your input is int a, it can match the int token and then the a letter, or the int a identifier, and it will choose the latter, the int a identifier. And if you write only ints, so that all interpretations are of the same size, RustLex will choose the action that was defined later in the specification. So in this case, if you write ints, it will say that it's so the int keyword and not the int identifier, because the rule for the int keyword was described later. And at the top of the definition, the rule here just eliminates things that are not needed, spaces, things like that. So they serve as separators between tokens. So you write this, you run the Rusty compiler, it will load the RustLex library, run a small piece of Rust code that I wrote that will generate deterministic finite automata from it, then pass back to Rusty Rust code that describes the transition tables of the automata and some code to iterate over it, and you're done. And then you can use this Lexer. So how do you use the Lexer? Well, the actions may cause the Lexer function to return. This is not the case in this example. In this example, once you match the token, you just print a message. But this is not what you want to do most of the time. Most of the time you want to return an object that describes the token you just saw, to be able to pass it later to a parser, to keep information about it. When you just matched a token that corresponds to the identifier regular expression, it's fine to know that you just saw an identifier, but you want to also know which identifier you just saw. It will be important for the rest of the compiler phrases. So generally, actions return something to say, I saw this thing. So I choose to give the generated Lexer an iterator interface, so that each call to the Lexer function will return the next token as an option token. Each time you call the Lexer function, it will start to where you stopped the last time in the input stream. It will try to pass the input stream with the set of rules, and once it is sure it matched the longest input possible, it will return some and with the token it matched, or if it didn't match anything, just return none, and this will cause the iteration to stop. Because in Rust, when you write something like for toc in Lexer, it will call the Lexer.next method till it returns none, and then stop. So here, it's the same example that on the previous slide, but instead of printing which token we just matched, we return an object to indicate what we saw. So, of course, in a real program, you would have to declare a type before the invocation of the RustLex macro. Currently, the return type of the RustLex function must be option token, and the token name must be token. It can be something else, but in the future it will be probably overridable in some way. And then in your main function, you create an input stream, you give it to the Lexer. I have no idea why it is a box reader, though. It was written a long time ago. And then you iterate over the Lexer, and each time it sees a token, it gives it to, oh, there's a curly brace missing. It gives it to the block you wrote in your for loop, and continues till the next method returns none, and then stops. I have other slides to talk about specific features of Lex and RustLex. They're not really very interesting, but I will pass on it quickly. Conditions are a feature when you cannot completely parse your language using only regular expressions. And it allows you to define another automator with manual transitions between the different automators. Instead of having a single state machine with transitions that are encoded into the transition table, you will have two separate state machines. And when you are into an action, you can say, okay, go to the other machine. And the other machine has a different set of rows to parse inputs. So a typical example of it, though conditions are not required for this specific example, but it's often used, it's comments. Because, yeah, for example, you might want to continue to count the lines of your program for error reporting while you are passing a comment. If you write a single regular expression that matches a whole comment, the generated analyzer won't do anything while it matches this regular expression, so you lose the information of the line breaks that may appear inside it. So you use conditions. You start to write, this is always the same example, except that C-like syntax for comments has been added. So when you see the beginning of a comment, you say begin, and you enter another automator, which is described under the comment identifier. In this other automator, it has been omitted here, but you may, when you match a line return, instead of doing nothing, increment a line counter, and when you see the end of the comment, you go back to the initial automator. There are a few other things. Named regex definitions is something like you have a few rules that use the same regular expression, and you don't want to have to type the word regular expression every time, so you can give it a name, but that's not revolutionary. Anonymous conditions is a tricky thing that I implemented that are useful if you want to include an action on the middle of a regular expression and you don't want to declare a condition because you would end up by writing a lot and a lot of conditions. But it's very buggy right now. I was expecting it to provide the ability to match, to extract the substrings that matches sub-expressions of the tokens, but it doesn't work very well right now. And properties are a feature that allow you to extend that allows you to extend the generated structure that stores the information about the Lexer with custom fields that you can then to which you can then assign in actions of the lexical analyzer. So, for example, if you want to implement a line counter, instead of declaring a global mutable variable like you do with Lex, you will ask RustLex to create a field for this in the generated structure. Things that remain to do, as I said, being able to extract the substrings that matched a given sub-expression of a token. This is currently, I said it was possible with the anonymous conditions, but it's very painful and very buggy. And reduce transition table size, because currently they are absolutely huge. They use they use as much space as possible input characters for each state of the machine. Lex uses something more clever to reduce their size, but it's not implemented in RustLex for now. So, yeah, thanks. If you have some questions. And if not, you are welcome if you want to contribute to this thing, because I don't know if I will continue to contribute actively on it. I was a bit depressed recently when I noticed how many things Raggle was able to do and how easy it was to do in Raggle. And since Raggle has now perfectly fine Rust backends, this project, my project, lost a bit of interest. But anyway, maybe if I have time, I will continue to improve it a bit. Thanks. Huh? No questions?